Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, now we reach at the chapter 4, Enterprise Modeling. This chapter is outlined based on the following objective and also this objective. During the requirement modeling process, as described in previous chapter, we use several fact-finding techniques to investigate the current system and identify user requirements. Now, we will use the information that gathered from that process to develop logical model. Logical model shows what the system must do regardless of how it will be implemented physically. Later, in system design phase, we will build a physical model. Physical model describes how the system will be constructed. There are many graphical techniques that can be used to describe an information system. One popular method is to draw a set of data flow diagrams. A data flow diagram uses various symbols to show how the system transforms input data into useful information. A data flow diagram shows how data moves through an information system but does not show program logic or processing step. In other words, a set of DFDs provide a logical model that shows what the system does, not how it does it. Basically, DFDs use four basic symbols that represent processes, data flows, data stores, and entity. There are two types of DFD symbol sets. You can use gain and Sanson symbol set, or you can use Jordan symbol set. In this class, we will use gain and Sanson symbol set. Symbols are referenced by using all capital letters for the symbol name. Look at this. Look at this example. All symbol names here are using capital letter. Now we will study each basic symbol in the DFD. First is a process symbol. A process symbol receives input data and produce output that has a different content for or both. Processes contain the business logic or also called business rules that transform the data and produce the required result. The symbol for a process is a rectangle with rounded corner. Look at this example. The name of the process appears inside the rectangle. The process name identifies a specific function and consists of a verb and adjective if necessary, followed by a singular noun. Example of process names such as apply payment, calculate commission, and assign final grade. In DFD, a process symbol can be referred to as a black box because the input, outputs, and general function of the process are unknown, but the underlying details and logic of the process are hidden. Next is a data flow symbol. A data flow symbol is a path for data to move from one part of the information system to another. It represents one or more data items. For example, a data flow could consist of a single data item such as student ID or IC, or it could include a set of data such as a class roster or application form. The detailed content of the data flow will be included in the data dictionary, which is described later in this chapter. The symbol for a data flow is a line with a single or double arrowhead. These are examples of correct combination of data flow and process symbol. From this example, we can see clearly the DFD still use the basic computing method, which must have input data flow, process, and output data flow. There are three data flow and process combinations that we must avoid. Firstly is a spontaneous generation. The process produces output but has no input data flow. Look at this example. The apply insurance process produces two outputs, policy number and payment amount. However, has no input data flow to process and produce the output. Secondly is a black hole. In this scenario, a process has input but produce no output. Refer to the second example. Here, the calculate gross pay is called black hole process because this process has input, which are hours work and pay rate, but no output produced from this process. And the last one is a gray hole. A gray hole is a process that has at least one input and one output, but the input obviously is insufficient to generate the output shown. For example, look at the third figure here. The calculate grade has date of birth as input, which is not sufficient to produce a final grade. The third basic symbol of the DFD is a data store symbol. It is used in the DFD to represent data that the system stores. The physical characteristics of a data store are unimportant because you are concerned only with a logical model. This part we will do during designing phase when you design the database. This symbol has a flat rectangle that is open on the right side and closed on the left side. Look at the example. A data store name is a plural name consisting of a noun and adjective, if needed. Examples of data store names such as student, account receivable, and purchase order. A data store must be connected to a process with a data flow. Refer to these examples. In this example, they show the data store has at least one incoming or input data flow and one outgoing or output data flow and is connected to a process symbol with a data flow. These examples show incorrect uses of a data store symbol in a DFD. In first example, two data stores, courses and students, are connected incorrectly because no process in between them. In second and third examples, the data stores lack either an outgoing or incoming data flow. And the last symbol in a DFD is an entity symbol or external entity symbol. The entity symbol represents in rectangle shape which may be shaded to make it look three-dimensional. Okay, look at the example. The name of the entity appears inside the symbol. A DFD shows only external entities that provide data to the system or receive output from the system. The DFD entities also called as terminators, source and sink. They are called terminators because they are data origin or final destination. The entities that supply data to a system are called the source. They are also known as sink when they receive data from the system. This slide shows the examples of correct and incorrect uses of external entity in a DFD. From these examples, we should understand each entity in the DFD must connect to at least one process. This figure shows a summary of the rules for using DFD symbols. If we refer to this figure, we can see any symbols of the DFD must connect to at least one process. You cannot connect directly, for example, external entity to external entity to data store, or data store to data store without process symbol between them. Now I will show you step by step to design a DFD. However, in this video, I just show the general steps and guidelines for designing it. I provide the PDF file to show the step by step how to design DFD using a few case studies. You can refer this file. You create a DFD based on your fact findings result, or if you have the case study, you create it based on the case study. Basically, there are three-step process in designing DFD. First, drawing a context diagram. Second step is drawing a diagram 0 DFD. Third step, if needed, is drawing the lower level diagrams. Before designing the DFD, let's review the guideline for drawing it. First, draw the context diagram so that it's fit on one page. Second, use the name of the information system as the process name in the context diagram. Third, use unique names within each set of symbols. This is important to ensure we deal the same symbol. For example, in your DFD of grading system, have one entity named student. Whenever you see the entity student on any other DFD in the grading system, you know that you are dealing with the same entity. Fourth, do not cross line. One way to achieve that goal is to restrict the number of symbols in any DFD. For example, on lower level diagrams with multiple processes, you should not have more than 9 processes. If more than 9 symbols, usually is a signal that your DFD is too complex and you should reconsider your analysis. Fifth, provide a unit name and reference number for each process. Sixth, obtain as much user input and feedback as possible. Your objective is to ensure that the model is accurate, easy to understand, and meets the needs of its user. The first step in designing the DFD is drawing a context diagram. A context diagram is a top-level view of an information system that shows the system boundaries and scope. To draw a context diagram, you start by placing a single process symbol in the center of the page. Identify it as a process 0. Process 0 represents the entire information system. Identify the entities and the name and content of the data flows and the direction of the data flows. Then you place the system entity around the process 0 and use data flows to connect the entity to process 0. A second step is drawing a diagram 0 DFD. Diagram 0 zooms in on the system and shows major internal processes, data flows, and data stores. Diagram 0 is an exploded view of process 0. Look at the example. This is the process 0 of context diagram for grading system. The details of process 0 we picture in diagram 0 for grading system. In other words, the details of process 0 is featuring in the diagram 0 and lower level diagram if needed. Diagram 0 also repeats the entities and data flows that appear in the context diagram. It must retain all the connections that flow into and out of the process. For example, in the context diagram, the student entities give the submitted work data flow to the grading system process. The student entity and submitted work data flow appear again in the diagram 0. Look at this example. Each process has a reference number. Look at here. All processes in diagram 0 have unit reference number. The DFD may have a diverging data flow. A divergent data flow is a data flow in which the same data travels to two or more different locations. Look at the example. A divergent data flow is the best way to show the flow rather than showing two identical data flows, which could be misleading. When you exploit a DFD, the higher level diagram is called the parent diagram, and the lower level diagram is referred to as the child diagram. When you create a set of DFD for a system, you break the process logic down into smaller units, called functional primitive, that programmer will use to develop code. A functional primitive is a process that consists of a single function that is not explored further. If needed, we will go to the third step, draw the lower level diagram. To create lower level diagram, besides rules of the DFD, you must use leveling and balancing techniques. Leveling technique is a process of drawing a series of increasingly detailed diagrams until all functional primitives are identified. While balancing techniques maintain consistency among a set of DFDs by ensuring that input and output data flows align properly. Leveling uses a series of detailed DFDs to describe an information system. Leveling technique also known as exploding, partitioning, or decomposing. This figure provides an example of leveling. Look at this figure. An order system consists of several processes. Using leveling, we start with an overall view, which is a context diagram with single process symbol. Next, we create diagram 0 to show more details of order system. In this example, the diagram 0 of order system consists of 3 processes. Then, we continue to create lower level DFDs until all processes are identified as functional primitives, which represent single processing function. In this example, process 1, field order process, actually consists of 3 processes. Verify order, process 1.1, prepare reject notice, process 1.2, and assemble order, process 1.3. Refer to the diagram 1 DFD. All processes in this diagram are numbered using a decimal notation consisting of the parent's reference number, a decimal point, and sequence number within the diagram. In this example, process 1 consists of several processes, so the reference number in diagram 1 DFD for process have reference number 1.1, 1.2, and 1.3. Let's say process 1.3 assemble order is decomposed further. The processes in diagram 1.2 the processes in diagram 1.3 would be numbered as 1.3.1, 1.3.2, and so on. Balancing ensures that the input and output data flows of the parent DFD are maintained on the child DFD. This example shows the DFD of all the system expands the contact diagram into DFD diagram 0 and DFD diagram 1. If we study this example, we can see this DFD still maintains the input and output data flows of parent DFD on the child DFD. Refer to the connection between customer entity and process 0 in contact diagram using order data flow. In the contact diagram, you can see the customer entity gives order input data flow to the process 0 or the system. This connection is still maintained when we design the diagram 0. Look at this part. However, in the diagram 0, the customer entity connects to the one of the processes in the system, which is field order process. Same goes when the diagram 0 expands into the diagram 1 DFD. Look at this part. The DFD still retains the connection that flow into and out process 1. Refer here. The DFD still shows the customer entity give order input data flow to the process in process 1, which is process 1.1 verify order. After designing the DFD, we need to prepare the data dictionary. The details within those DFDs are documented separately in a data dictionary. A data dictionary or data repository is a central storehouse of information about the system data. An analyst uses the data dictionary to collect, document, and organize specific facts about the system. Also defines and describes all data elements and meaningful combination of data elements. A data element, also known as a data item or field, is the smallest piece of data that has meaning. Data elements are combined into records, also called data structures. A record is a meaningful combination of related data elements that is included in a data flow or retained in a data store. The more complex the system, the more difficult it is to maintain full and accurate documentation. Fortunately, a modern case tool such as Visible Analyst Case Tool simplify the task. However, if you don't have the case tool like Visible Analyst Case Tool, you can use other alternatives such as Microsoft Word as long as you can record all details of the DFD. It is important to document every element of DFD in the data dictionary. The data dictionary can be a reference to everyone who involved in the system development to understand the details of the system in depth. The objective of data dictionary is to provide clear, comprehensive information about the data and processes that make up the system. Next, the slides will show the attributes usually recorded and described in the data dictionary. For example, to document the data element name, alias, type and length, and default value are the attributes that should be recorded in the data dictionary. This is an example of how to document the data elements. For data flows, the attributes that usually recorded are data flow name, description, alternate name, origin, destination, record, and volume and frequency. These are attributes always recorded for data store. Normally, we record data store name, description, alternate names, attributes, and volume and frequency. For processes, normally we record the process name, description, process number, and process description. The attributes of entities in data dictionary are entity name, description, alternate name, input data flows, and output data flows. Okay, this slide shows the attributes of records that usually exist in the data store, which may record or data structure name, definition or description, alternate names, and attributes. In the data dictionary, the attributes of records that usually exist in the data store, which may record or data structure name, definition or description, alternate names, and attributes. In conclusion, we can say the data dictionary serves as a central storehouse of documentation for an information system. A data dictionary is created when the system is developed and is updated constantly as the system is implemented, operated, and maintained. You can obtain many valuable reports from a data dictionary as listed on slide. Process description tools. A process description documents the details of a functional primitive, which represents a specific set of processing steps and business logic. Using a set of process description tools, you create a model that is accurate, complete, and concise. Examples of process description tools are Modular Design, Structured English, Decision Table, and Decision Tree. Modular design is based on a combination of three logical structures, sometimes called control structures, which serve as building blocks for the process. I'm sure all of you are familiar with the modular design, which this topic you have learned during in part 1, so I don't intend to explain further. Basically, the modular design consists of three structures: sequence, selection, and iteration or looping. Another process description tool is a structured English. Structured English is a subset of standard English that describes logical processes clearly and accurately. These two also you have learned in part 1, so we will not study too details about it. A decision table is a logical structure that shows every combination of conditions and outcomes. Analysts often use decision tables to describe a process and ensure that they have considered all possible situations. This example shows a decision table based on the sales promotion policy. The sales promotion policy is gathered from the fact-finding activity. From this policy, we found a few combinations of conditions to produce certain outcomes. For example, if the answer of this question are yes, which are preferred customer, ordered more than 1,000 and use our charge card, then the outcome should be the user gets 5% discount and additional 5% discount. A decision tree is a graphical representation of the conditions, action, and rules found in a decision table. Decision tree show the logical in a horizontal form that resembles a tree with the roots at the left and the branches to the right. Look at this example. Decision trees and decision tables provide the same result, but in the different form. So, whether to use a decision table or tree often is a matter of personal preference. A decision table might be a better way to handle complex combination of conditions. On the other hand, a decision tree is an effective way to describe a relatively simple process. Although structure analysis tools such as Dfd and flowcharts are used to develop logical model for a new system, these tools also can be used to develop physical model of an information system. A physical model shows how the system requirements are implemented. Sequence of models. Many systems analysts create a physical model of the current system and then develop a logical model of the current system before tackling a logical model of the new system. Performing the exercise step allows them to understand the current system better. Many analysts follow a four-model approach, which means that they develop a physical model of the current system, a logical model of the current system, a logical model of the new system, and a physical model of the new system. The major benefit of this approach is that it gives you a clear picture of the current system function. However, this approach may add time and increase cost needed to develop both physical and logical model of the current system. Okay, that's all and thank you.